Hello viewers, today we start this lecture number 4 on eccentric connection. In this lecture we have to learn about welded eccentric connection. Welded eccentric connection are the same as bolted eccentric connection, that is, in one type of connection the movement will be parallel to the plane of the welds, and in other the movement will be perpendicular to the plane of the welds. Now we take first type of connection, movement in the same plane as the weld as shown in figure first. The movement is the same plane as the weld. In this first type of connection, this weld is subjected to two kinds of forces, that is shear and torsion. To analyze and design this type of weld, we calculate the shearing stresses developed in the weld resulting from the force P and torsion. This is our figure 2. Now we first calculate shearing stresses due to the direct force P. Q1 is the shearing stresses due to direct force P. Q1 is equals to P upon twice of B plus D multiplied by T, where B is the width of weld as shown in figure second, D is the depth of weld, and T is effective throat thickness, which is taken as K into S, where K is constant depending upon the angle between the fusion faces, and we have to calculate the value of K from the table 22 of IS 800, and S is denoted as weld size. Now the second step, we will calculate the shearing stresses generated by twisting movement. Twisting movement is T equals to force multiplied by eccentricity. This shearing stress is greater in welds located farther from the center of gravity of the weld group. This shearing stresses due to torsion will be larger at this point, say that is C point, because it is farthest from the CG of the weld group. The maximum shearing stresses due to torsion is given by Q2 equals to torsion multiplied by R maximum upon polar moment of inertia IP, where polar moment of inertia is given as Ixx plus Iyy. In third step, we have to determine the resulting shearing stresses for Q1 and Q2. QR equals to Q1 square plus Q2 square plus twice Q1 Q2 cos theta, where theta is the angle between Q1 and Q2 as shown in figure. This is theta is the angle between Q1 and Q2. So we calculate resultant stress from this formula. And in last step, we have to compare resulting stress to the design strength as given in the IS code. That is, we have to compare that resultant stress then design strength as per given in IS code. Then QR, if QR is less than Fu upon root 3 into multiplied by gamma MW, hence the design of weld is safe. And if QR is greater than design strength of weld, redesign the welded connection. So we take an example. Determine the maximum load that can be resisted by the bracket shown in figure by fillet weld of size 8 mm if it is shock welding. This is a diagram. We have to calculate in this question the force P. and given as weld size 8 millimeter. We have to given weld size equals to 8 millimeter, assuming that K value is 0.7 from table number 22 of IS 800 and FUW ultimate strength in weld is 410 Newton per mm square. So our first step is we have to calculate effective throat thickness, which is T equals to Ks. We are assuming that K equals to 0.7 multiplied by weld size, then effective throat thickness comes out to be 5.6 millimeter. Second step, we have to calculate total area of weld. This is 150 multiplied by 5.6 and 150 multiplied by 5.6, hence twice of 150 into 5.6 plus 300 into 5.6 equals to 3360 millimeter square. In second step, we have to locate the CG of weld group. Due to symmetry, XX will pass through the center of the weld. XX is passed through the center of the weld geometry. Now we take moment of area about AB face of weld. This is your AB face of weld. We have to take moment about that portion. We get 150 into 5.6. It is act as center and distance of this from AB face is 75 millimeter. So AX bar is twice into 150 into 5.6 into 75. The area of weld is 150 into 5.6. There are two times the area because this is one and there is second weld of same area multiplied by the 75, which is distance between CG of area of weld to the AB face. Then we have to calculate X bar is 7.5 millimeter. In fourth step, we have to calculate the extreme distance. That is point C of weld from CG of the weld group. So this is R maximum. This distance is 150 minus 37.5. That means 112.5 plus this is 150 square, that is 150 square. Then R maximum comes out to be 187.5 millimeter. In fifth step, we have to calculate moment of inertia of weld about centroidal axis. IXX is 50.4 into 10 raised to power 6 millimeter raised to power 4, and IYY we have get 7.875 into 10 raised to power 6 millimeter raised to power 4. Then we have to calculate polar moment of inertia, which is IP equals to IXX plus IYY. It is equal to 58.275 into 10 raised to power 6 millimeter raised to power 4. In next step, we have to calculate direct shear stress due to load. That is Q1 equals to P upon 3360 Newton per mm square. In next step, we have to calculate shear stress at extreme corner due to torsion Q2, torsion multiplied by R maximum upon polar moment of inertia, and it is comes out to be P upon 1243.2 Newton per mm square. In 8th step, we have to calculate resultant stress, where theta is angle between Q1 and Q2 from figure 3rd, and in this case we get cos theta equals to 0.6. Hence, QR is P upon, we get resultant stress equals to P upon 988.755 Newton per mm square, and then equate this strength to the design strength, that is Fu upon gamma mw multiplied by root 3. Here for shop welding, gamma mw is taken as 1.25, and when we equate, then we get P equals to 187.241 kilonewton. It is a factor load. Then working load is calculated as 187.241 upon 1.5, and it is comes out to be 124.827 kilonewton. And this is your exercise. You perform this exercise. Next time we take second type of welded connections.